Good morning, everyone. How are you doing today? We're with the gear-based Quasi continuous variable transmission system. My name is Martin Soto. This is Chris Adu. That's Kyle Russell. Unfortunately, Justice and Daniel weren't able to be here, but let's go ahead and get started. Nowadays, a lot of emphasis and money and time has been put into clean energy, and it's good and all, but we decided to go into the whole wind energy, right? I mean, obviously. Because what better thing to do that we have free wind every day, we have it all the time, so we went ahead and went for that. The purpose of this is to have our wind turbine work at an optimum regime. That way we can get the most money, the most efficiency out of it. In today's wind turbines, they use power electronics in order to maintain a constant output so that the generator can create a current, because a generator has to work at a certain hertz, a certain frequency. That way it would always make the energy. But with the power electronics, it's very costly. It takes a lot of time to install, and then it breaks down pretty easily. So what we decided to do is replace all the electronics with something mechanical, something continuous, something that will work more, and it'll be more efficient, and it'll last longer. So our solution is to introduce a continuous variable transmission. This allows the wind speed to just rotate freely at wherever, whatever it may be, and then our mechanical parts, our transmission will change gears and all that stuff, and it will allow it to have a constant output without all the breaking down of all the electronics and all that stuff. We won't have to worry too much about how much it costs and stuff like that.
Our design is essentially a gearbox with a large number of discrete gear ratios. It transforms a variable input speed into a constant output speed. Our design includes five central gears located along a central input and output shaft, and five compounded satellite gears located between every two central gears. The central gear 1 is attached to the input shaft. The central gear 5 is attached to the output shafts, and central gears 2, 3, and 4 rotate freely. The power is transferred from the input shaft to the central gear 1 and then through the compound gear A. It is then transferred through each central gear and compound gear until it reaches the central gear 5, where it is transferred to the output shaft. This is our design. As you can see, on the left there is a motor, and on the right there's a generator. The motor simulates the wind speed. The red gears are the central gears, with the one on the left being central gear 1. The other different colored gears represent the 5 sets of compound gears located between every two central gears. The blue gears are the compound gear A's, and the black gears are the D compound gears.
Okay, so basically our transmission creates one representative gear ratio. So we have a lot of different choices along each stage to select different gear ratios, but each of those gear ratios is determined by the number of teeth of the input gear over the number of teeth of the output gear. But basically our QCVT system is just a final representative gear ratio that's the set of ratios is we said we had a large number, and they're discrete ratios, so they're very close together, so we can account for very small changes in wind speed. The number of gear ratios that we have is just a function of the number of satellite gears and the number of compound gears. The number of central gears.
Our design has a total of 625 separate gear ratios. The gear ratios range from 11 to 48. There are a couple of different parameters that help determine help you find what particular gear ratio you want. You can change the number of teeth on a gear, and second, you can vary the diametral pitch of a gear. Our system has gears with diametral pitches of 6 and 3. And the diametral pitch is essentially the number of teeth per inch.
Betts's law states that we can only extract 59.3% of the power of the wind with a wind turbine. That power can be represented as a function of rho, the density of air, A, the cross-section area created by the blades, and V, the speed of the wind as it approaches the blades. We stated earlier that we want to create the optimum efficiency for our turbine. And so we introduced the power coefficient, CP, which is a ratio of the power that we harvest from the wind and the power that is actually present in the wind. And so by introducing CP and also the tip speed ratio lambda, which is the ratio of the speed of the rotor of the turbine and the speed of the wind, we can create a control law. So we maximize CP with respect to lambda, and we obtain our optimum values of CP and lambda, and we can maintain those values in our turbine by allowing the rotor speed to vary proportionally to the wind speed. And by doing so, for each increasing wind speed, we can harvest more power. So here we show as the wind speed increases from 5 to 12 meters per second, the amount of power that we harvest from the wind increases greatly. The torque of the turbine can be expressed as a function of the power coefficient and the rotational speed of the turbine. And through this equation, we can actually introduce our gear ratio with the gear ratio, the speed of the generator is equal to the speed of the turbine times the gear ratio that our QCVT creates. So by introducing that into the torque that is put on the generator, we can also progress with our control law. Our turbine can be controlled in several ways. So our primary control is our QCVT, our variable gear ratio. And so our control law for that is stated here in the bottom right corner. Our gear ratio that we select is K times the generator speed to the 2/3. And so K is composed of several different parameters that are specific to the turbine and to each wind speed. And so, like I said, as the wind speed changes, we have a new K and a new gear ratio. We also can control our turbine with torque control. However, that's costly, and it costs money to do so. You lose customers for the power that's being generated by the electricity generator. And so that's not something that we really want to do. And also, blade pitch control is another control we can use, but we only use that for a safety factor in high wind speeds.
This is some exciting stuff here I'm about to tell you. We want to know how close we're gonna get to that actual continuous variable transmission, right? So we did a study about generators and the way the energy is produced. We wanted to have, because the generator produces energy at 60 hertz, we wanted to get as close as possible into that range, right? So we chose, as you can hear, we chose some wind speed, variable wind speeds, starting at 30 and ending at 50. That way, we have a wind speed at 30 to 50, it could be 35, 36, 41, whatever, and we have a desired speed ratio. That desired speed ratio is what we need in order to make those 60 hertz happen, right? This is the output speed that's gonna give us, that we need for the 60 hertz. It's gonna be at 1,000 RPM. So we have here, you can see we have the input, the desired gear ratio, and then the output, All of that is going to give us 60 hertz, right? And here we have the actual ratio that we use with our CVT. Say we wanted a speed of like 30, right? Our CVT is going to change gears and stuff like that, and it's going to give us an actual speed ratio, gear ratio. Here's the actual output speed, and then here's the cool part here. We got so close to those 60 hertz at within 0.5%. That's really close. I mean, there's some spikes here and there, but those can be adjusted. We're going to talk about it here soon. But 0.5% in that range of the 60 hertz. And generators usually work at 0.5%, you know, so the closer we get to it, the better it is. And we got really, really close. So that's some exciting stuff there. All right, just to conclude, we show that the generator has to be a constant output speed. It has to be at 60 hertz. Whatever ratio it has to be, that our CVT is going to work for it. The diametral pitch in our CVT, the number of gears, the number of stages, all of that can be adjusted. It's a really, really flexible machine. So wherever it is that you are, whatever wind speeds that are out there, you can adjust our CVT in order to accommodate for that. So wherever you need really, really high speeds or really, really low speeds, our turbine will be able to adjust for that. Also, the control out that we stated is pretty good. We eliminated all the power electronics, or most of them at least, and with our CVT, it's going to give us that optimum regime. Also, spur gears have been used for like a really long time. You know, ever since, I don't know, decades now, perhaps, since the invention of the car, even before, you know. So why not use it? It's worked this long, why not use it? You know, it's very efficient, and it's really, really easy to maintain. You know, if one of them breaks, you just put in another one, you know? So why not use it? Also, the most important part about this whole thing is the money. You know, we all want money, you know, the power companies, they want that money. So with this, they're gonna save a lot more money, but they're gonna get more money. So it's a win-win situation, you know? And just for some future work, obviously we're at a prototype right now. We want to include a torque converter and a synchronizer. Now, what is that for? The synchronizer, if some of you guys may know, it's used in manual transmissions in order to shift gears, you know? And here we're gonna have, even though it seems kind of odd, we're gonna have a synchronizer, but it's gonna be an automatic synchronizer. So that way the gears can change automatic. The torque converter, that's gonna diminish the amount of like spike in the change of gears, you know, so it will be smoother. So that way that 0.5% that I talked about earlier will even be smaller, you know, so it'll be even more efficient. Also, you know, we want to propose some actual controls, better controls, so that way we could, you know, again, get more efficient. You know, that's the word here, more efficient, you know. And these are some of our references. We would like to acknowledge Dr. Slim Massouz. He's our instructor. He's been with us since the beginning of the year. He's, you know, helped us through. He's, you know, made us, you know, work harder than we were expected. But hey, that's okay, because we like that. We also like to acknowledge Dr. Wayne, because, you know, he's provided, you know, with the budget that we have. We like to thank, you know, especially thank Mr. Weller. Man, he's helped us out a lot, and his assistant, Dane Dallas. Any questions?
Going back to the results, when you guys were trying to get within the 60, can you explain the testing that you did?
Oh, this is not actual physical testing. This is just
the
theoretical
mathematical,
testing.
okay.
Yeah.
So you haven't actually made.
We have a prototype. It's just we're still putting it together.
Okay.
It's just a lot of components, and it's just time.
And so then you'll compare to see if the results.
Right. Exactly.
The synchronizer that you guys are hoping to put on, is that going to allow it to change with the wind speed without other technicians or someone having to change it?
That's exactly, so the control system combined with the synchronizers, we've kind of got some ideas on that, but the controls and the synchronizers together will allow it to change based on, it'll take a measurement, whatever the wind speed or the speed of the rotor is, and then our controls will switch the gears for us, and nobody has to be there physically to actually change.
45 gears in our current design. 40 being the satellite gears and 5 central gears.
Questions?
Any other questions? Thank you very much.